Hi, this is problem 3.6. This problem is from the book Pierre and Johnson from Equilibrium of Particles. It's a coil, which is this right here is A. It's frictionless. The constant of the spring is given and is equals to 4 pounds per inch. And they want us to find the weight of the coil if the equilibrium position is given. So here is the initial position. We release that coil and the coil goes down and is in a new position. Let me draw it with a different color right here. H2, this is H1, for 16 inches. So it goes down 4 inches. And then it stays in equilibrium. So the new position of this coil is right here, right? And then, therefore, we have another position, and the spring is now stretched, so to say. So if this is the unstretched length of the spring, this will be the final length of the spring, and this will be what it got stretched. We can call it delta. The free body diagram, that's always our first step. We will do the free body diagram of the coil A, right? We have the active force, which is the weight of A, in this case, is an unknown. And as you see, we have this tension over here, which is a reactive force. We have the tension. Let me call this tension, this is the pulley is B, so I will call it the tension AB. And as you see, in order to be the system in equilibrium, it cannot move, right? So if I leave the free body diagram like that, it will move to the right because this tension is pulling the coil to the right direction. So what is preventing this coil to move to the right? This bar over here. So I always have to put the reactive force of any device that is preventing motion. So anything that prevents motion creates a reaction in my free body diagram. So here I have a reaction R, which is the reaction between the coil and the bar over here, which the coil is sliding. And of course, I always have my coordinate system X and Y, and I need this angle over here. I don't have that. So, since they want us to find that weight, I need that tension, because here I have three unknowns. I have the tension, which is the tension of the rope. I have the reaction with the bar, and I have the weight. When I analyze the pulley over here, right, since this is a frictionless pulley, I can say that this tension over here, the tension over here, right, which is the same tension AB, is this tension over here, right? So this is tension AB, and this is the force of the spring. And of course, I have these two reactions that hold the pulley. But what I'm analyzing here is these two tensions are equal. So I can say that the tension of the rope is equals to the force of the spring, because this is an ideal pulley. And I know that the tension of the spring is the constant times the S. The S is what the spring stretches, right? You remember that? That is the final length minus the initial length. And I call it that, this delta over here. So we have to find that delta. How much is that delta if I know that the coil went from 12 inches down to 16 and it stopped there because the spring through this cord was able to hold that weight. So how do I find how much did the spring went up? And as you can see, I have here this hypotenuse, let me call it H1 in capital letter, and then I have H2. The difference between this H1 and H2 will be how much did the springs go up. So how much is H1? H1, since this is a right triangle, will be equals the square root of 12 squared plus 12 squared, which is equals to 12 square root of 2. How much is H2? H2 will be equals to 16, and the base of this triangle is the same. And if I calculate that, this gives me 20 inches. So this is 12 inch, 20 inch. So what I was able to stretch that spring is the difference between those two. So that delta is equals H2 minus H1, which equals to 20 minus 12 square root of 2, which is equals to 3.03. And that delta is actually what we were able to stretch the spring. Therefore, the force of the spring is equals to that K times delta, which is 4 times 3.03, which is equals to 12.12 pounds. Now that I have the force of the spring, now I apply the equations of equilibrium. I do not care about finding the reaction between the coil and the bar, because what I want to find is only the weight of that coil. Therefore, I'm only going to do my equation of equilibrium in the y direction. And that will be equals to the tension, which is the force of the spring, times the sine of this angle minus the weight of A. But I was able to find the force of the spring, but I need to find that angle. Which angle is that one? This is this angle over here. And as you see, let me write it over here. I have this distance is 16, which is the height, and this is 12. This is this angle. Therefore, theta is tangent to the -1 of 16 over 12. And I have that angle over here, and this is equals to 53.13 degrees. I could also use my sine as 16 over the hypotenuse. As I said, you can use either finding the angle or finding in the geometry. This is the H2 is 20. Okay, finally, we got that the weight is equals to the force of the spring times the sine of that angle and that gives me a weight of 9.69 pounds. And this is the solution of this problem. Just to recall, we did our free body diagram and we noticed that we had too many unknowns. So we did the analysis of the pulley and noticed that the tension was equal to the spring. And then we had to find this force of the spring. And to find the force of the spring, we need to find how much the spring has been stretched. And we found it through analyzing how much this went down.